Think about it. You're streaming a 4K movie. Your phone's blowing up with notifications, you're on a video call, all at the same time, and not a single wire in sight. How does that even work? Well, today we are pulling back the curtain on that invisible magic that powers our entire connected world, Wi-Fi. All right, let's get into it.
So, have you ever actually stopped to wonder how the internet just flies through the air? I mean, we don't just go online anymore, right? We're literally swimming in a sea of invisible radio waves that are carrying everything from our emails to the latest binge-worthy show right through the walls of our house. It feels like magic, but today we're going to break down how it actually works.
To really get it, we've got to start with the absolute basics, the signal itself. This is the real foundation of, well, all wireless communication, really. So at its heart, Wi-Fi is just information. That's it. It's information hitching a ride on electromagnetic waves, specifically radio waves. What's happening is your computer's wireless adapter takes all that digital data, the ones and zeros, and it basically translates it into a radio signal. Then an antenna just blasts it out into the air. It's really no different than how an FM radio station sends music to your car. Your router is just sending data through the air. And it all boils down to the properties of that invisible wave. Okay, so every single wave has something called a frequency. And really, that's just a fancy way of saying how fast it vibrates up and down. A signal that vibrates kind of slowly, that's a low frequency. One that's buzzing super fast, that's a high frequency. You can picture it like ripples in a pond, right? Some are slow and really wide apart, while others are fast and all bunched up together. Right, so if frequency is how fast the wave is wiggling, then wavelength is how far it actually travels in one of those wiggles, from one peak to the next. Now, these two ideas are totally linked, and they are absolutely key to understanding how your Wi-Fi really works, which actually brings us to our next slide. Okay, this is where it gets super practical for your network at home. Think of your Wi-Fi like a highway system, and it has two main roads. First, you've got the 2.4 gigahertz band. This is kind of like the local road. It can go a longer distance, and it's way better at getting through obstacles like walls. But the downside is, it's slower and it gets totally jammed up with interference from stuff like your microwave or cordless phones. Then, you have the 5 gigahertz band. This is the superhighway, or way faster with a lot less traffic, but its range is shorter. So here's the takeaway. If you're gaming or streaming, you absolutely want to be on that 5 gigahertz superhighway as long as you're close enough to your router to get a good signal. Okay, so we've got all these radio waves flying around. How in the world do our devices make any sense of it? I mean, how does my phone talk to your router? Well, they need a common language, a set of rules. And in the world of Wi-Fi, these rules are called the IEEE 802.11 standards. They're set by this group, the Institute of Electrical and Electronics Engineers, basically to make sure a brand new phone from one company can talk to a 10-year-old router from a totally different company. It's all about making sure everyone's speaking the same language. And you can see the evolution of that language right here. It's pretty wild. Back in 1999, we were getting 11 megabits per second, which was okay for slowly loading a web page, I guess, but every new standard was a massive leap forward. The jump to 802.11n and then AC, that's what made streaming HD video even possible. And now we've got Wi-Fi 6, or 802.11ax. And what's cool about this one is it's not just about raw speed. It's about being able to handle dozens and dozens of devices in a super crowded home without everything grinding to a halt. So we've got the invisible signal, we've got the rules of the road, but what's the actual piece of hardware that's making this all happen? Well, that would be the access point, or AP for short. The access point is basically the bridge. It's the translator. It takes that wired internet connection coming into your house or office and translates it into the wireless signal that your laptop, your phone, your smart TV, all of that can understand. You know that box your internet provider gave you? Yeah, that thing is a router, a switch, and an access point, all crammed into one. Okay, so one AP at home, super easy, no problem. But what happens when you're at a university or a huge hospital or a massive corporate campus? You might have hundreds, maybe even thousands of these access points. How on earth do you manage all of them without going completely insane? And yeah, this is the fundamental problem for any big organization. You can't just log into each AP one by one to update the software or change a Wi-Fi password. It's just not going to happen. It would literally be a full-time job for a whole team of people. And this exact problem is what led to the development of these different ways to manage networks, what we call network architectures. And to make this super easy to understand, we're going to use a simple analogy. Think of managing your APs like you're managing a chain of coffee shops. Trust me, this makes the different ways of doing it crystal clear. All right, first up is the autonomous architecture. This is your classic independent coffee shop. The manager, which is the AP itself, is really smart. We call it a fat AP because it has all the intelligence built in. It runs the whole show. You configure it all by itself, and it just does its thing. This is perfect for your house or tiny office, but try to manage 100 of these? Yeah, it just doesn't scale. Next up, the controller-based model. Okay, now we're a big coffee chain. We've got a corporate headquarters. The individual shops are now what we call lightweight APs. They're kind of dumbed down. They just focus on serving the coffee, or in our case, passing the data. All the big decisions, the menu changes, the pricing, that all comes from the central headquarters, which is the wireless LAN controller. This is called a split MAC architecture because the thinking is literally split between that central controller and all the APs out in the field.
And finally, we have the modern cloud-based approach. This is like having your coffee chain's headquarters not in a physical building, but up in the cloud, accessible from anywhere with an internet connection. The APs on site are still smart, but all of their configuration, monitoring, and updates are pushed down from a central online dashboard. This gives you incredible flexibility, especially for businesses that have offices all over the country or even the world. So, which one is the right one? Well, it really depends. This table kind of breaks it all down. For a small office or your home, autonomous is perfect. Simple, gets the job done. For a single huge campus, like a university, controller-based is still king. It's powerful and centralized. But for a business with lots of distributed sites, like a retail chain, cloud-based offers the most flexibility. At the end of the day, it's all about choosing the right tool for the job.
Okay, we've covered the signal, the rules, and how we manage the whole thing. But there's one last super critical piece of the puzzle that dictates how that signal actually travels through the air, and that's the antenna. Oh, I love this analogy. It makes it so clear. An omnidirectional antenna is basically a light bulb. It casts its signal out in all directions, a full 360-degree donut shape around it. This is perfect for filling a typical office or a conference room with Wi-Fi. A directional antenna, on the other hand, is like a spotlight. It focuses all of its energy into one single narrow beam. This is exactly what you'd use to, say, beam a Wi-Fi signal across a parking lot to connect two separate buildings together. And to squeeze even more performance out of our Wi-Fi, modern systems use this really clever trick called MIMO. That stands for multiple input, multiple output. Basically, by using multiple antennas to send and receive data at the same time, it can dramatically boost your speed and reliability. The best way to think about it is like adding more lanes to a highway during rush hour. More lanes means more cars can get through at once, and with MIMO, way more data can get through at once. So we've gone all the way from these invisible waves to massive global networks that can be managed from the cloud. It's incredible, but here's the thought I really want to leave you with. Wi-Fi was originally designed for things like laptops, devices that use a lot of data. But now, we live in a world of smartwatches, thermostats, smart light bulbs, and just countless tiny little sensors. How is this technology going to have to change and adapt to serve billions, literally billions, of tiny devices that just need to send a little blip of information every now and then? That, right there, is the next great challenge for Wi-Fi.